So thanks again for inviting me to chat with you today. And I'd like to talk with you a little bit about the revolution that's happening right now in robotics, and in particular in autonomous robotics, which is going to fundamentally change, I think, transportation, and not just transportation on the ground, which we talk about, but also in air and space. And to do that, I want to zoom back a little bit in time. I'm one of those folks who actually grew up before we were all heavily using the internet to live our lives. And so I'd like to talk a little bit about what the internet revolution did for us, and then draw some parallels to the robotics revolution. So first of all, real quickly about me, thank you for the introduction. It's been an interesting 2 decades with the last 7 years in autonomous robotics, and then moving over into the space industry where I've been working on autonomous robots that go to space. So let's talk about the information revolution. Revolutions fundamentally come with big technology changes, which then affect new products, new experiences, create new ecosystems and new markets. And so if you rewind back to 1999, there was this early idea of the digital hub. And so just to frame things a little bit, if you think about what we had on our local computers versus what we had on the internet over in the World Wide Web, for example, our email, the internet was basically for either cruising around websites or transmitting emails from one local machine over the network to another local machine. And all of our music and our video and our games and our work were all located on our computer locally. And what was interesting, in 1999, Apple came out with this computer called the iMac DV, and DV stood for digital video. And it was because there was this inkling in 1999 that digital video was going to be a thing. And what was going to enable that was the internet was going to get fast enough that downloads would get a lot faster, uploads would get a lot faster, and people would actually want to create digital videos and stream them online to others. And so if you fast forward to today, there's been this huge move where all of these applications, enabled fundamentally by this connectivity infrastructure, by broadband, have moved off of local devices and have moved up into the cloud. And so now all your media, all your work, many of our games are all now up in the cloud. And really what we have locally are very kind of custom portals, like physical portals that map to the user application at the time. So for at home or at work or on the go, you have things like a smartphone or CarPlay or Android Auto for a car, for example, and you have your desktop. But these are very kind of bespoke portals into the internet, and then all your information sits in the cloud. And what that has done is really unlocked a whole new economy and ecosystem of applications that nobody could have imagined back in 2006. And if you think about the other piece of it, is that it's all enabled by connectivity. And so you have portals on one side, physical portals on one side, and on the other side, you have all of these services that are enabled for linking us not only to our devices, but also to each other. So if you think about all of the various different services that fundamentally have enabled our social lives to exist in a virtual world and connect folks from literally across the planet, which is a pretty amazing thing. If you think about the robotics revolution and everything that promises, it's this idea that fundamentally we're going to be able to not be driving and instead get that time back to do other things. And that's an amazing promise. And if you think about what that does on land, you can imagine in the air, you don't need pilots anymore. If you imagine in space, you have autonomous vehicles in space. But today's reality looks like this. These are 2 companies, robotic vehicles that are driving around today. And you can just by staring at it, you don't need to know anything about robotics to know that this requires a tremendous amount of evolution, a tremendous amount of simplification, not just on the AI side, which we'll talk about in a little bit, but in the simplification, in the integration, to get to something that fundamentally can have a supply chain that enables scale. And so let's talk a little bit about what goes into an autonomous robot. The first is great parallels to a human system, because humans are autonomous, right? So the first is that vehicles need sensor systems. Humans use our eyes, we use our ears, we have motion sensing in our inner ear. And so the ability to sense the world around you is really important. The second is you need computation. You need the ability to interpret all of that information in the world, classify it, make predictions about how the world is going to evolve over time, over the next few moments, and they make decisions about what you want to do next. And then the way you act on those decisions is through actuators. And so that can be hydrofluidic or mechanical actuators in a vehicle. It can, for humans, obviously, it's our muscles. And then that whole thing is underpinned by a power system. Vehicles require engines or require batteries. Spacecraft require batteries. Airplanes require jet engines. Maybe someday the future of airplanes will be electric or hybrid electric. You need power systems to underpin all of it. There's one more thing, though, which is connectivity. And connectivity is an interesting thing because today it enables humans to work with other humans. For robots, it actually enables them to get much more useful contextual information. So you hear things about like HD maps, for example, that provide all sorts of information for autonomous vehicles on the road about what to expect beyond what their sensors can see. Where are the stop signs, where are the stoplights, where are the lanes, all those kinds of things. However, with robotics, there's something that's more important, or kind of two more factors that are often not considered by humans when they think about their internet connectivity. One is reliability. The way to think about this is we just all went through months of working remotely and having our kids go to school remotely. And if you lose, Comcast goes down at your house, the worst thing that happens is your Zoom goes down and you're no longer able to connect to class. Maybe your kids go out and they eat food from the refrigerator they shouldn't have or get distracted, but that's kind of the worst of it. However, with robotics, the loss of that connection fundamentally means that you don't get map tiles. If you've got remote human operation to assist an autonomous robot, be it one that's in the air or in space or on the ground, you lose that connection. You lose any cloud processing, so any functionality that you were trying to offload to the cloud, that's now gone. And so your robot just got a lot dumber. And so if you aren't going to have reliable connectivity, the bar for what your robot needs to be able to do locally is just orders of magnitude higher. In addition, there's availability. And, I experience this every time. I live in California. And so every time I try and drive from the San Francisco Bay Area down to L.A., where there's like Disneyland and Legoland and stuff like that, and of course, if you drive further south, you get down to UC San Diego, there are all sorts of areas where there just isn't wireless connectivity at all. And of course, my kids complain about not being able to play their videos on their iPad. But imagine that you're a robot relying on all of this information that comes from the cloud, and you now have driven into a dead zone. So that starts to block out places where autonomous vehicle can't even go. And so fundamentally, you need both reliability and availability in order to have a great system. Another example is, imagine you're a farmer and you want to control your farm equipment, but it just so happens there isn't this wireless connectivity in the area where you have your farm. You can't really just pick up your farm and move it. So how do you get great, reliable, and available connectivity everywhere? And actually, a connectivity hub in space makes a lot of sense for that, because it's got a really great wide field of view. It's first order resilient to weather. It runs on solar. So once you've got it up there, it runs continuously on renewable energy, which is great. However, there's some major issues with that. One is you need to get it up there in the first place, and then it needs to stay up there and in the right place and pointing in the right direction. And so, in other words, you need the ability to put an autonomous space robot into space, and then it needs to be there. And in order to provide ubiquitous mobility, or sorry, not mobility, but connectivity, it needs to be cheap. It needs to be scalable. And so when I think about that, I go back and I go, okay, well, thinking about Earth and thinking about space, what are the challenges for each? Well, an autonomous robot on Earth obviously needs to be able to read road signs, deal with bad actors, which is a huge AI problem. In space, you have radiation because you don't have the protection of the atmosphere. You have thermals, again, because you don't have the protection of the atmosphere. So there are unique challenges for each. But interestingly enough, there's an incredible amount of overlap, because both need to be able to perceive, need to be able to decide how to navigate and what they want to do autonomously. Both have actuators that control the position and the pose of the vehicle. They both require power systems, and they both really require highly reliable and highly available connectivity. And so it's amazing to me how much overlap there is. And so to make this autonomous robotics dream a reality, the first is automation, right? There's a ton of work that has to happen in AI and algorithms, and then making those algorithms performant, which means making them really, really efficient. The second is sensors, and a big piece in sensors is really driving to solid state, because with solid state will come reliability, will come scalability. So that's key. Compute. So we've been watching computers become more and more powerful from a computational standpoint while requiring less electrical power. That trend needs to continue. And part of that is designing computers that are really specific to solving the automation kind of problem, as opposed to just general processing. Available and reliable connectivity, we talked about. Power, this is an interesting thing where there's kind of this virtuous cycle going on that was first powered by mobility, driving smartphones and tablets and things and laptops to have longer and longer battery life and useful video time and call time and internet browsing time, which is really driving batteries to be a lot more efficient. Similarly, the autonomous vehicle industry and the battery electric vehicle industry are driving the power technologies to improve dramatically. Also, with renewable energy, that's been driving the solar technologies also to become a lot more efficient versus time. And that's going to enable everything from spacecraft to be a lot smaller and lighter, to things like airplanes, to things like autonomous vehicles. Materials are key, especially when it comes to sustainability. One of the challenges with some of the really high performing materials like carbon fiber is that it's very challenging to recycle them. And so figuring out what the material sets are that are both recyclable as well as highly manufacturable are going to be key. And that's part of why you see a lot more moves towards utilizing aluminum, because it's fundamentally recyclable. You have to build up supply chains in order to enable scale, and that starts with raw materials, as we were talking about earlier in today's talk, through the ability to integrate those raw materials or fabricate those raw materials into parts, integrate those parts into assemblies, and eventually build complete systems. And then lastly, with robotics, because it creates, we're creating a product that actually interacts in the real world. It's not just moving photons of light and making sound by modulating air molecules. It's actually moving around in space. There's a tremendous amount of public and private partnership that is needed in order to make sure that these products deliver tremendous value, but also do it very safely. And, you know, in the autonomous vehicle space on Earth and in the air, you don't want those vehicles behaving badly. In space, you don't want to create space junk, and you don't want to interfere with other vehicles. So you've got to put all these pieces together in order to actually have a complete scalable product and unlock that new economy. So I would like to tell you a little bit about a place that I've been at recently, which is working on autonomous space vehicles. It's called a company called Astra. It's located in the Bay Area. And this photograph is actually of the launch site that Astra has up in Kodiak, Alaska. And part of why I wanted to show this to you is because it's not much. It's power, it's data, it's concrete pad, and it's a fence. And that's not usually the image folks have when they think about launching stuff to space. But this is the vision of Astra, which is really using technology to fundamentally change the story around small satellite launches by really shrinking the entire footprint of what's required. The other thing that's, I think, key about Astra that I found really exciting was that the company is focused on Earth. Astra's not worried about going to space. I care much more about how do I improve life on Earth from space, because I think we're going to be around here for quite some time. And so what do you need in order to put an autonomous vehicle into space? Well, you need the keys to space. You need a launch vehicle that actually can get payloads from the surface of the Earth to space. And so I'd like to show you a cool video that kind of describes a little bit about what it takes to actually get there. So the keys to space, we got there, we got to space, not quite at the velocity we wanted to be at. So we were close. And this summer, we'll actually be launching and delivering our first commercial payload to space. So I'm super, super excited to do that. So then the question is, all right, well, you got the keys to space. Well, that's like kind of getting the keys to the car. It's really like tough. You work really hard to like get your driver's license, you get your car, you get insurance, and then it's like, well, where are you going to go? And suddenly, like the fact that you have keys and you have a vehicle turned out to be like not the most important thing. And so that's when you start to think about spacecraft. And this has been an area where I've been thinking really hard. And I'd like to talk to you a little bit about what I think the spacecraft of the future really are. The first is that a spacecraft already is an autonomous vehicle. And a rocket, even a multi-stage rocket at the end of the day, is an autonomous vehicle that gets you to space. So why carry two brains to space? You might as well have the spacecraft fly the rocket. I think that makes a lot of logical sense. The second is, and this is partly enabled by the fact that we're really focused on low Earth orbit, the spacecraft of the future are going to heavily leverage the tech from commercial, automotive, and consumer technologies. So we talked about batteries, same story with low power compute, same story with sensors. There's just a tremendous amount of synergy here that I think the industry's waking up to. The next is that it's really going to provide worldwide broadband. It's going to provide that ubiquitous availability, high availability and high reliability connectivity. And it's also going to enable, sensing and Earth observation. And so we're going to learn a lot more about how our Earth works and what our impact on it is. And then hopefully we can learn some solutions out of that will be very powerful. In addition, there will be IoT. So we'll have connectivity to our infrastructure anywhere and everywhere. And then lastly, I think low Earth orbit is going to be a really big deal. And part of the reason why I think low Earth orbit is a really big deal is not just because of low latency and high bandwidth broadband that comes with being in a low Earth orbit, but also because it allows us to really focus on not leaving space garbage. When you're in low Earth orbit, you're close enough in that you can basically maneuver your satellites such that it will self-deorbit by dragging on the atmosphere when its useful life is over. And that way you're not leaving junk up in space and ending up with kind of like that terrible WALL-E future that we don't want. We want a very clean space future. So to do this, though, again, requires scale. Scale is what innovation makes innovation matter. This is a quote from one of my favorite folks to quote, which is Reid Hoffman, who's one of the founders of LinkedIn. And, that scale is key because it enables you to have the impact you want. Just showing one of something doesn't actually deliver the impact. One iPhone would not change the world. But thinking about just zooming out and going like, okay, well, what's the recipe for success? Why are companies that innovate sometimes successful and sometimes not? And I think there's a few general rules that are key. The first is seeing around corners, looking at where the market's going to go to, seeing what supply chain we're going to need, seeing what technologies we're going to need, seeing what applications customers don't even know to ask for yet. That's our job. It's the innovator's job. It's to see around the corners and aim to where the puck is going to be. The second is using every tool at your disposal. So globally optimizing, thinking about hardware, software, services, putting all of this together in a way that really delights customers and makes the world a better place. Doing that and solving technical problems, mastering those really critical technologies at a scale that allows for mass production. So it's not just solving that point technology solution, it's solving the whole supply chain problem and integration problem is the thing that kind of makes a market difference between a great idea and an impactful great idea. And lastly is velocity. The ability to learn quickly is really important. So, when I think about, the future of transportation, it's really from anywhere to anywhere. And that's from anywhere on Earth to anywhere on Earth. That's from anywhere on Earth to anywhere in space. It's also this theme of, if you look back over the last 20 years of going from mainframe computing to mobile computing and what that means about integration and what it means about simplification. Globally optimizing, thinking about what the key enabling technologies are and doubling down on them. and really thinking about platforms. How do we create platforms that enable a new ecosystem? We had no idea that by creating an amazing mobile product and the power of the connectivity of the internet, we'd unlock this entirely new application and connectivity ecosystems. And then lastly, operational efficiency is key. Great ideas need to be backed by great execution. And so if you do those two things, I think you really have a winning recipe. And so I'll just make a shameless pitch for my company really briefly. Astra's hiring. Come join us, astra.com/careers. But really, I'm just looking forward to seeing when we unlock this new economy and this new ecosystem through innovation, through a new supply chain, what all the developers and the engineers and the innovators and supply chain managers and everybody who's involved in like making this real, what they create, because it's really up to them. So with that, I'd just like to say thank you very much for taking the time.